So good morning, everyone. I'm here to present our work on routing attacks in Bitcoin. This is joint work with Laurent Van Bever and Aviv Zohar. Routing attacks quite often make the news. You will have probably heard about this Russian ISP that hijacked large chunks of internet traffic destined to MasterCard, Visa, and other financial services. Or about this other Canadian ISP that managed to steal $83,000 from a mining pool by hijacking its prefixes. However, this is only the tip of the iceberg of routing manipulation. By analyzing 6 months of BGP data, we managed to find that hijacks are in fact much more prevalent in the internet today. In the y-axis of this graph, you can see the number of hijacks that we detected as the number of in each of the months that are shown in the x-axis. We found that multiple thousands of hijacks occur every month. Of course, not all of them are malicious. In fact, most of them are misconfigurations. But in any case, they are practical, and they do affect internet traffic today. The purpose of our work is to shed light on the impact of routing attacks in Bitcoin. Intuitively, Bitcoin should be robust against routing attacks, right? After all, it's a highly decentralized network of nodes that are scattered around the globe, establish random connections, and even use multi-homing or other additional overlay networks to interconnect. Unlike intuition, though, Bitcoin is highly centralized from both the routing and the mining viewpoint. To give you an intuition of our results, in the y-axis you can see the cumulative percentage of mining power as a function of the number of networks hosting it. Clearly, mining power is centralized to few networks. And you can think of a network as AT&T, for example. Notice that 68% of mining power is only hosted in 10 networks. Similarly, if we look at the cumulative percentage of Bitcoin traffic as a function of the number of networks intercepting it, we again see that Bitcoin traffic is centralized. This time, 63% of Bitcoin traffic is only intercepted by 3 networks. So, due to these characteristics, 2 attacks are practical and effective today. The partition attack, in which the attacker splits the network to half, and the delay attack, in which the attacker delays the block propagation. The partition attack is feasible, as the attacker needs first to hijack prefixes, but is also very effective, even against the Bitcoin network as a whole. The delay attack is completely invisible, as the attacker only acts on traffic that she naturally intercepts. However, it's only effective against targeted nodes. My talk is composed of 4 parts. First, I will give you some background information. Then I will talk about the 2 attacks in detail, and I'll finish the talk with countermeasures. So let's jump to the background. Bitcoin is a distributed network of nodes that establish random connections. Each of the nodes have a ledger of all transactions ever done in Bitcoin, which we call the blockchain. The blockchain is a chain of blocks that is extended by miners who use a lot of computational power for this, and they're paid for their job via block rewards. Miners collaborate, forming mining pools, which are multi-homed. Bitcoin connections are routed over the internet, which is composed of smaller networks, which we call autonomous systems, or ASs. BGP is then responsible for computing the forwarding path across them. Bitcoin messages are propagated unencrypted and without any integrity guarantees. As such, any AS in the forwarding path could eavesdrop, delay, drop, or even modify the messages. Note that this is even possible if the Bitcoin traffic is encrypted, as in this case, the AS in the AS path, in the forwarding path, would still be able to distinguish and drop the Bitcoin messages. I will now talk about the first out of the 2 attacks that we consider, namely the partition attack. The goal of the partition attack is to split the Bitcoin network into 2 disjoint components, such that no information can be exchanged between them. The impact of such an attack is worrying. First, it's an effective denial of service attack, as transactions can no longer be propagated. Second, it can cause revenue loss, as all blocks mined within one of the 2 components will be eventually discarded, together with the pool's rewards. And finally, during the partition, Bitcoins can be spent twice, allowing for double spending attacks. So let's see how it works. Assume that the AES in the middle is malicious and wants to split the Bitcoin network into the left and the right components, as denoted by the red line. As an intuition, the attacker will try to attract all traffic destined to nodes in the right. To understand how this is done, we'll focus on node F, which is the green node in the right corner of the slide. I will now describe how the attacker can attract all traffic destined to the green node using BGP hijack. F, the green node, has an IP, which belongs to its provider, namely AES6. AES6 is responsible for informing the internet about a prefix that covers the IP of AES6. To that end, AES6 will create a BGP advertisement, which will be propagated AES by AES until all of them learn a path to the prefix. For instance, AES1 will learn the path via AES7 and then AES6. BGP, what is important to note here is that BGP does not check the validity of advertisements. As such, any AES can advertise any prefix. So let's assume that the attacker actually advertised a prefix that covers the IP of the green node. Note that the advertisement of the attacker is more specific, as it's /24 compared to the /23 of the benign advertisement. Since all routers in the internet prefer the longest prefix match, they will actually use the malicious advertisement. As such, all traffic destined to the green node will be routed via the attacker. This is called the BGP hijack, and this is exactly what the attacker will use to create the partition. She will hijack all traffic destined to nodes in the right side. She will then drop all the connections that breach the partition, and boom, the partition is created. In practice, creating partition is, of course, not that easy. There are partitions that are actually infeasible to be created, and that's because there are connections which the attacker cannot intercept. There are three kinds of such connections: connections within a mining pool, connections within an AES, and private connections between mining pools. Even in this case, the attacker will detect that the desired partition is infeasible and will instead build a similar but feasible one. In the paper, we explain the exact algorithm that the attacker will use to do this, and we also prove that the attacker will always manage to isolate the maximum feasible subset of nodes she initially wanted to isolate. We evaluate the partition attack in terms of practicality and time efficiency. To evaluate the practicality of our attack, we first had to infer the actual Bitcoin topology, which we augment with routing information. Using this, we found that splitting mining power even to half, which is the worst case scenario for Bitcoin, can be done by hijacking less than 100 prefixes. Looking at it in perspective, a hijack of 100 prefixes is negligible compared to the hijacks that happen in the internet every day. As an illustration, this graph shows the maximum number of prefixes that were hijacked at once in each month. As you can see, hijacks of up to 1,000 prefixes are frequently seen in the internet today. We also evaluated our attack in terms of time efficiency. For that, we measured the time required to perform a partition attack by attacking our own nodes. For this, we hosted few Bitcoin clients at ETH, which were connected to the actual Bitcoin network and whose prefixes we advertise ourselves by Amsterdam. As such, all traffic destined to our nodes was actually routed through Amsterdam. Next, we attacked our own nodes by hijacking their prefixes via another BGP peer, which was located in the University of Cornell. We then measured the time required for all traffic to our nodes to be diverted from the initial benign path via Amsterdam to the malicious path via the Cornell University. We summarized our results in this graph. In the y-axis, you see the cumulative percentage of connections that were intercepted by the attacker as a function of the time this took. We found that it takes less than 2 minutes for all traffic to be intercepted by the attacker, which means that it would take less than 2 minutes for the partition to be created. On the other hand, it would take hours for the partition to be resolved, as it will take hours for the hijack to be resolved. It took even Google 3 hours to manage to mitigate the famous Pakistan hijack in 2008. That's because it's a human-driven process. I will now talk about the second out of the two attacks we consider, namely the delay attack. The goal of a delay attack is to keep the victim uninformed of the latest mined block. The impact of such an attack is worrying and it depends on the victim. An uninformed merchant, for example, is susceptible to double spending attacks. An uninformed mining pool will waste its computational power mining on something that is destined to be discarded, while an uninformed regular node is unable to contribute to the peer-to-peer network. So let's see how it works. In this slide, you can see 3 Bitcoin clients. Nodes A and B connect to the victim, and the attacker intercepts the traffic between node A and the victim. Now let's assume that a block is mined in the Bitcoin network, and nodes A and B learn about it and advertise it to the victim via an inventory message. The victim will request a block from only one of its peers, as instructed by the Bitcoin protocol, via a get data message. If the attacker wants to prevent the victim from getting this block, she could drop the get data message. Alternatively, she could drop the block message itself when the block is delivered. However, in practice, that's not that easy. And that's because both of these attacks will actually fail because Bitcoin runs over a reliable transfer protocol, namely TCP, that will abort the connection if specific packets cannot be delivered. However, the attacker can change the content of the get data message such that a different block is requested. In this case, node A will happily deliver the block, and the victim will ignore it and will in fact wait for 20 minutes for node A to deliver the block. So far, the attacker managed to keep the victim uninformed of the latest mined block for 20 minutes, which is an enlarged time interval for Bitcoin, taking into consideration that blocks are only mined every 10 minutes. After the 20 minutes timeout, the victim will assume that node A is malicious and will disconnect. If the attacker wants to prevent this, she can still trigger the delivery of the block via converting a get data message of a transaction to a get data that requests the actual block. If the block is delivered within the 20 minutes timeout, then the attack is completely invisible and the connection is kept alive for later use. We evaluated our attack in terms of effectiveness and practicality. To evaluate our attack for effectiveness, we had to implement it in the wild. So our victim node was again connected to the actual Bitcoin network, and we assumed that only a fraction of its connections were routed via the attacker. Using this setup, we were able to find that the attacker can keep the victim uninformed for most of its uptime while staying completely under the radar. And that is even true if the attacker intercepts only a fraction of the victim's connections. Using this setup, we found that if the attacker intercepts 50% of the victim's connections, then the victim will stay uninformed for 60% of its uptime. And to understand how practical this attack is today, we again looked at the actual Bitcoin network, and we found that for 70% almost of the Bitcoin clients today, there is at least one AS-level adversary that can perform this attack in practice. And note here that we did not even consider the direct providers of the victim as possible attackers. I will finish the talk with countermeasures. So, luckily, both short and long-term countermeasures exist. Short-term countermeasures can be deployed today, but are less effective. For instance, a Bitcoin client could select its peers in a more routing-aware manner, such that no single ISP intercepts a considerable percentage of its connections. This will automatically make our node less vulnerable to delay attacks. Similarly, the node could monitor the behavior of its peers to detect anomalies such as increased delay that might indicate a partition attack. On the other hand, long-term countermeasures require protocol or infrastructure change but are much more effective. For instance, end-to-end encryption would protect Bitcoin clients from delay attacks, but not from partition attack. Similarly, the deployment of secure routing protocols such as BGP-SEC or Scion would indeed protect Bitcoin clients from partitioning attacks, but not from delay attacks. With this, I finished my talk. I will quickly summarize. So today I showed that Bitcoin is vulnerable to routing attacks, and their potential impact is worrying, and that countermeasures exist, some of which can even benefit early adopters. We have a website. Please check it to see our code and also to learn more about the project. And now I'm happy to take questions.
We have 2 microphones.
Hello, my name is Armin from UT Arlington, and I was wondering, how did you determine the AS level path between nodes?
Okay, so nodes have an IP which you can find in regular websites. This IP will drive you to the AS of that this node is located. And then to infer the AS path between them, you have to use the AS level topology. For example, Kaida has some public data for this. And using algorithms, taking into consideration the economic relationship between the AS, you can find the AS path.
Okay. Also, for the partition attack, to hijack 100 prefixes, how many ASs must be controlled by the adversary?
The hijack will be initiated only by one AS. So everyone with access to a BGP network can actually do it. So you only need one ISP, only one AS.
Only one AS?
Yes.
So does that assume that all the connections in the entire network go through one AS?
So what the hijack will do is attract all traffic destined to the prefixes that you hijack via the AS through which you hijack. So initially, the connections will not be routed via the AS that you hijack, but once you hijack, that will be the case.
Okay, thank you.
I noticed that you did this with the cooperation of an AS rather than, you're not claiming to have broken BGP security. Do I understand that correctly?
I'm not sure I understand the question.
You have a cooperating AS for doing this.
Yes.
You're not saying that you actually corrupted the routing without permission.
No, you need to have access to an ISP. So an ISP is an...
So I wondered if you had any comments on what the actual feasibility is for is an insider within an AS, I guess, could do that, or do you have any comments on BGP security in and of itself?
So based on our analysis in 6 months, we found that thousands of prefixes are hijacked. That means that it is possible to actually hijack traffic, like prefixes are hijacked every day. And that's a problem of the BGP itself. So I think it's quite practical based on that.
Alin Tomescu, MIT. Thanks for your talk. I really like your work. I was wondering, you mentioned that a partitioning attack led to funds being stolen from a mining pool, you said?
Yes.
I was wondering if you could tell us more about that. I'm really curious how that happened and how money could be stolen with a partitioning attack.
It was not with a partition attack, but rather with routing attacks in general, meaning with a hijack. So in this case, what the attacker did is she managed to hijack prefixes that were important for the communication between the miners and the Stratum server that the pool was using. And using that, they were able to kind of use the computational power of the miners that belong to another pool.
Thanks. One last quick question.
Morning. David Smith, Ripple. Thank you for the talk. How do you foresee the Bitcoin ecosystem responding to these threats? The long-term measures require changes to the protocol. Do you foresee the Bitcoin forking?
Well, I will, for example, if you're talking about end-to-end encryption that I mentioned, I can only comment on that with respect to the routing attacks and not a general thing. So yes, for example, large difference in the way the protocol operates would help against routing attacks. For example, if you take end-to-end encryption, that would help because AESs in the AES path will no longer be able to tamper the message. However, we also have short-term countermeasures that can still be deployed. They don't require a fork and would still make a huge change to how vulnerable Bitcoin clients are. So to sum up, yes, long-term countermeasures are important and it would be nice to be deployed, but that's not the first thing that you could do.
All right, let's thank Maria.